These sets normally would come with an environment that you would then modify for your particular use.
And that was the thing that I found the most interesting about this was that Reagan described that they have about 70 different policies that come with this system. And that is got to be something that I was just asking him, do you have a list somewhere of all of them other than we did a less of the file that showed, all of these policy points, but we were just talking about getting that up in their documentation, because I think that's something, even if for whatever reason one didn't end up wanting to use IRODs, that kind of having thought through what are the policies about managing data is something that I think seems really interesting and shareable. The system also seems to allow people to create their own rules for operating on, any given file or collection. And we were talking also about the work that's going on right now to talk about kind of understanding and sharing those rules. Because again, I think what was impressive to me about this system was that not having to necessarily recreate the wheel. That there's kind of, it's created an engine for managing all sorts of things that seem to me to be very common across all of the different kinds of data that we've kind of heard about today. And then this idea of how you then help people if they can also arbitrarily create their own sets of actions on their files, again, those might be, something someone else would want. And so that to me was one of the interesting things coming out of this project.
One of the differences is that the focus of this environment is actually management. It's actually understanding how you're controlling, manipulating, making assertions about your data. So it doesn't focus on the issue of discovery,
right,
but it does provide the mechanisms that allow you to add metadata to support discovery and ensure that each item has the required metadata attributes. And therefore, the other challenge it had to face is it had to work across administrative domains, work across different geographical locations, work across different networking technology, because there are people who move around multi-terabyte files in this environment, and then work at scale, meaning international collaborations from the Far East to the US to Europe. At scale meaning petabytes of data, at scale meaning 10,000 users, at scale meaning moving data at the maximum line rate. So you have to move large collections very rapidly using parallel I/O.
I know we were talking a little also about some of what they're supporting to allow discovery layers on top of this, and it's already, you're saying, integrated with DSpace and Fedora at this point, or not?
DSpace and Fedora are
and they're doing it via
that sit on top.
Right, that's what I'm saying. So, and what was it? A Kubra, you were saying, which was
Kubra is a standard interface.
The standard interface they
Fedora
were using, right?
To interact with.
So I'm sure that there are other discovery interfaces that could also go on top of something like this.
So, a quick synopsis.
Okay, next I think questions on policy-based data management or questions particular to IRODS or IRODS implementation. Anyone?
What are the biggest challenges facing policy-based management?
We're going to do one more level of virtualization. We virtualize files, virtualize collection, virtualize users, virtualize storage. We have to virtualize metadata. So I need to be able to take a metadata name as a unique item and associate properties with it, such as an authoritative URL or URI, comments, and then map from there to how it's being used.
Reagan, have you done any work to relate IRODS to meeting some of these certifications like data seal of approval or TRAC or ISO 16363?
Yes. So I worked with the RLG, NARA, TRAC, ISO 16363 groups. You should be able to take the ISO trustworthiness assessment criteria and turn them into roughly 100 rules that the system would automatically enforce for you. Once you've done that and you got an audit from them that yes, those rules work, you would then have a vehicle which would be able to send to anybody for enforcing trustworthiness.
wholesale, like wholesale certification, all of the criteria, or just some of them? Like,
It's all the computer actionable criteria.
right, yeah.
It wouldn't be the whole thing, but it would be everything.
Right, there are some things like you have a mission statement that includes preservation as part of the machine actionable, but there are other
Maybe you
things
could
like,
make a rule for that would blow up the whole system if you didn't have a mission.
Fees and permissions.
Exactly. They would just keep asking you until you did it.
but there are some criteria, like is your operating system up to its current level of patches, for example, that would be very machine actionable.
Correct.
Yeah, cool.
But you could also look at policy sets like HIPAA and FERPA for compliance. And the HIPAA policy set is about 250 rules.
Reading, the other thing I was trying to make that you mentioned was that you thought some about software preservation and from the workflow perspective in IRODs. And our group was talking about that. That might be neat to mention.
Yes.
As an aside for our group's benefit.
So one of the challenges is virtualizing workflows so they will work across any architecture. And what we had to do in our system is, because we're talking to many different types of storage device, a standard operational microservice doesn't issue I/O protocol. It does an intermediate protocol based on POSIX I/O. And then we map from that intermediate protocol to the actual protocol of the storage system. So the microservices will run on Windows, they'll run on Mac, they'll run on Linux, they run anywhere. They're operating system independent. That makes it reasonable for me then to look at migration as the creation of a driver that talks the new protocol, and then everything I did in the past continues to work.
More questions? All happy? Okay, I guess we're ready to hear from our big data group.
So big data focused on big data backed with big experiments with complicated analysis and reduction chains, because they were all Henry physicists here. And that's all they can talk about.
Or at least they talk the loudest.
I guess the preliminaries are these 2 points, right? Is that both with things like, Atlas and CMS, CDF and D0, also with things like the dark energy survey, these are large enough and the instrumental acumen is assembled that the fundamental reductions that publications are based on are almost always right. And so the use case of, I don't really believe what was published, I'd kind of like to redo it, is not the strong use case. The second, because that sort of stuff is verified by other experiments doing similar things and finding consistent results. And at some level with particle physics, today's discovery is tomorrow's calibration quantity, right? So people get more and more, successive generations of experiments have more capabilities. So in our discussion, what we came up with is that in this use case, the big data is actually accompanies a very large analysis system that took many people to assemble, was at the state of the art or for its scale for the time it was constructed, and that the systems tend to be built with in kind of a federated manner because they're big collaborations, people bringing pieces, people having somewhat independent technology choices, and there's a whole and so they're organized in a way that they're hard to sustain, and often they have factored into them facility class infrastructures, and the example in this case was an Oracle database. And so on the other hand, the nature of high energy physics is such that it's a statistical science and you're comparing distributions. The particular development of the art in high energy physics is that one has to produce a sample data set based on simulations, and one basically assumes that it occurs in the detector, applies the detector signature to it, and runs the whole data acquisition chain against it in order to get the 2 distributions to compare to see if the physics, you have a null case and a case where the new physics might arise. And so it's a struggle to take a system that when it was constructed is deemed at the state of the art, and many cannot be constructed, is constructed in kind of a federated software and systems building process that has diverse components. And now the question is, once the big army that built it went away, and once, of course, it's not, Moore's law has run a few cycles, and it isn't the biggest thing in the world anymore. How does one sustain it? Because one has to sustain a substantial fraction. The other part of the complexity arises because of the business processes of a very, very large collaboration. Initially, when a big experiment runs, a whole tier of work occurs on the data where data are prepared for reuse by many, many people. And this is an economy of scale that happens in a 2,000-person physics collaboration. Central groups do the initial instrument signature removal. Central groups do the initial reprocessing, and they build a system that has satisfactory economy of scales for while the experiment is serving 2,000 people. But that system may not have economical scaling when one scales it down to the use case. The use case under question is when you do not have 2,000 people actively investigating it, but you have, say, university groups that are interested in pursuing a physical topic. One actually has to kind of factor out. So one all of a sudden wants, instead of a standing infrastructure that's going to last for 10 years, one wants a stand-up infrastructure that would last for the duration of the investigation. And another difficulty faced in this thing is doing that factoring of you have a system that is built for one kind of enterprise and business process, and now you want to convert it to another. And so it has baked into it a different social structure of support for the people doing the investigations during the lifetime of the system. And that also tends to lead to big infrastructure and also specialized procedures for mass production that are not needed and become baggage for the inflation for reinflating a system to do stand-up and do an analysis later on in the system. The as-is state of it is that at the moment, these difficulties are handled by host laboratories retaining enough staff to keep these systems running at some sort of reduced rate. And the first goal would be to actually make systems work well enough in that environment, and then finally to make them be more portable, perhaps, and more stand-up, and able to be stood up more easily. What's wrong with that?
I thought that was awesome.
that was a wonderful piece of writing. Can you make sure you get that to?
I think it got recorded.
Yeah, we got to put that. That's got
recorded.
Got it.
I could try, but you guys were producing our first round of data. I'm so busy.
So two questions for you, Don. So I think you pointed out at the beginning that the likelihood that somebody's going to want to reanalyze the data because they suspected somebody's made a disaster in the publication is unlikely.
Right.
And maybe I missed it, but I didn't catch. Did you say after that what the expected use case is?
Yeah, the expected use case is you're looking for a new phenomenon.
Looking for a new phenomenon.
And in high-energy physics, to look for a new phenomenon, what you basically do is you produce some simulation with some new physics baked into it. And this is like, I'll make a zillion collisions, and this is the junk that will fly out.
Yeah.
Then you run that through the whole system, saying, oh, what would the detector have actually taken given all these particles were produced? And so when you do a comparative study in high-energy physics, you're basically running the data through a virtual detector with some model that would see what the detector would see and what it wouldn't see. And so to do the comparative study, you're effectively running a virtual version of the whole experiment.
So I think that's going to connect, that bears on our software discussion, in which I think the goal of reproducing past software and past data is not necessarily to reproduce exactly the analysis that was done, but to bring the old analysis codes back forth and reconfigure them to your new purpose.
Exactly. Yeah. I think for things this big, when the taxpayers pay that much money, I think the results are almost always good.
Huh.
That is.
You didn't say that. You didn't tie it to money.
Let me say that strongly. Right? When people make that kind of investment, they expect correct.
There's a lot of cross.
Right. And I don't think you're allowed to grow to do that kind of experiment unless you have the field has a history of being good like that. Right. I don't think you get to arrive at that kind of big science without ramping up bit after bit after bit and convincing people.
Yeah, so I'd like to propose an alternate viewpoint. What you're really doing is feature detection. You've gone through your simulation and said, here's the feature that I'm looking for. Is it actually present in the data? And when I discover it, I can then say, yes, I succeeded, the experiment verified what I expected to see. And if I'm trying to do new physics, then I'm looking for a new feature based upon however it's modified by the experimental apparatus. Can I take your data set and extract from it the identifiable features and then ask if all of these identified features are explained by current theory?
Would you like me to answer that?
Yeah, it's over my pay grade.
Yeah. So yes, completely. In fact, we've done it before. There was a project, I think it was called Quero, which did exactly this. It looked at pretty much every single distribution that they could think of and every single relation between n objects, where I think n was less than 4, so which for us is a lot. Made all of those plots, compared what was actually observed in data, and tried to compare it to what was expected if there was no new physics, and then just started to look at the differences. And I think there must have been about, this was on CDF, do you remember this? It's something like, I don't know, 1,000 plots, and something around 30% showed significant differences, which meant that what that's telling you is that this is not worthwhile, because those 30% are all going to be detector and simulation issues. You have a specific problem.
But as your equipment improves,
Okay, so what really improves is your method of calibration. So many of those issues, many of the reasons you see those discrepancies are because no one has looked at this particular distribution, because from a physics point of view, it's not thought of as interesting for whatever reason.
Yeah.
And the result is no one has spent any serious time understanding the detector's behavior when, say, you have two electrons that happen to be very close to each other. Right? We really have this case down where the electrons are far apart, but close together, we don't. And so if you sort of look at the continuous, you would expect, okay, well, it should all be good. It turns out when they're close together, we totally screw up, because nobody has really looked carefully at the detector response when you have. So those are most of the reasons why you see those discrepancies. The other thing is that it turns out is that kind of an analysis is never as sensitive as an analysis where you take a look at the new physics and you look at basically the theoretical underpinnings of what produces that new physics. You use it to predict a set of distributions. So what are the important distributions? Well, it turns out in this new physics, these two electrons will always be this far apart, just like that angle exactly. Okay, so now I create a new feature in name of my new physics, which says the electrons are exactly this far apart. So I have to invent a new feature. I don't know ahead of time, before I look at the new physics theories, what all the features are. So I need to have the ability to go back and extract a new feature that I previously had not thought about from the data.
but it tells you a way to migrate your results forward in time, because you've examined the entire phase space and you know which portion of the phase space you had.
But I think that's the key, is that I don't know that I've examined the entire phase space. I need to be able to go back and...
You have to stimulate the detector like nature would have stimulated it
Right.
to remove the instrumental signature.
Exactly. Or put it back in.
Yeah. But it says that there are multiple things to look at within this process, and then evaluating the results and their internal consistency is.
There are certainly a class of types of physics that we could look at where we only had the very high level results, the features, and would not need to go back and create new features. There certainly are classes of physics, but then there are also quite a few where we would have to go back and do something brand new, and it would need me. We would need to go do something with the simulation.
So the other thing I wanted to jump on was the scaling down observation. So I'm going to make a proposition here, and maybe this is for everybody who's involved in production, maybe to reaction to this. If our goal is to make the data useful again in 10, 15 years, based on the scale down observation, it seems to me part of the output of this project will be to define the data that we're going to keep in the assumption it could fit in one simple relational database, or something simple like that. To define the data model and the set of queries you might want to run against. Because 10, 15 years from now, there will be some I'm grossly simplifying here, but something along those lines. And to have the ability to run one simulation independently of all the distributed infrastructure that's currently in place to enable that. And if you have the data model, a means to query that data model in the simulation, then we've done our job in preserving the essential capabilities. Because 10, 15 years from now, there isn't going to be an LCD, at least not in the form of it is now. How does everybody feel about that? How does everybody feel about that proposition?
It's a very nice high-level summary, but the devil's in the details. I mean, for example, in order to run, I need my calibration data, which will be in a separate database. So I've now added a fourth bit on,
okay.
And I'll keep going, and I'll probably add a bunch more bits on. So at the high level, I think that summary makes sense, but you have more of these sort of satellite processes you have to create in order to do the...
And at least in some of our previous discussions, sometimes it's a little tricky to tease out the infrastructure from the essentials.
Yeah, I'm not...
Is that...
Yeah, I would say that's true, and I think that's partly a function of the fact that there's probably no one person that knows everything, so it's also a matter of the people you have in the room at some level. And the approach that we're taking, for example, at D0 to this is we're just trying it, where there's nothing except for those 3 bits. There's some data, there's some software, and we're trying to run on the data, and it fails. Okay, so this means we need this other bit, so we absorb the other bit. So it's kind of, that's how we're trying to learn. You know, there are pieces we can predict, but there are also connections that people have forgotten about because it was 20 years. It's been so stable. It was 20 years since the last time someone looked at it.
Yeah.
So,
but
I mean, does that answer?
One difference, though, Gordon, is that the LHC was set up intrinsically to be distributed, to run in a distributed environment.
Yeah, that's true.
And for that reason, it's actually helped us a bit. I mean, I think that we can hermetically seal off and probably detect all the external dependencies, and I don't think there are going to be that many. But what I do worry about is maintaining the ability for the software to remain functional. I mean, capturing what we actually need to keep the software sustainable going forward. I mean, it's not going to be the situation where we're porting 20 million lines of code every 6 months, or every 2 years to a new platform. We're not going to be able to do that. And there's just there's so many packages written by people who are, even long gone already from the experiment. So
thousands of people are authors of this software.
Organizations are roughly 500 people, and none of them are trained in software engineering or computer science or anything like that.
Let alone data preservation.
There are a few, what we call software professionals. Usually they're people who've been working in integrating software from the experiments for a long time. But anyway, the interesting thing is how do we, if we want to be able to read this data at some point in the future and keep it usable, we have to figure out where we actually cut, what do we actually have to capture going forward. And I wouldn't trust being able to read anything, a couple of years from now if we weren't actually actively testing it all the time. So it's almost like we need a framework that is, we have to sort of keep the data alive going forward. We can't let it sit. We have to do some level of testing and continuous reading, I think.
Now, are you talking about in terms of preserving the data or preserving the software stack, or both? I mean, some sort of continuous integration process.
I don't even think of it as the software. I mean, I think it's a software stack. I always think of it as the environment, so including basically the platform.
But I think the idea of a continuous integration test is probably a very good model.
Yeah.
So you can do that within virtualized environments too, so you can capture.
That's of course what we're thinking. Like along these lines, there's some kind of something that's capturing the environment, virtualizing it, and keeping it running going forward, so that we sort of have this place where we look and whenever there is an exception where it's no longer working or something, we know about it when there's at a time when we can actually do something about it.
That's a good
move on to
segue to
the-
your group, I
yeah.
think.
So you're not going to like what we talked about.
Because it's not continuous integration.
So the question I put before the group is, our goal is to ensure that 10 years from now, the data can be consumed in a usable way by appropriate software. And that can come in many forms, which might be as literal as running the exact bits that were running 10 years ago, or running equivalent software, somehow maintaining that capability. And so I'm going to do this a little bit out of order, but we talked about the space of problems that results here, and it primarily comes from the fact that you've got a stack of things that are continuously evolving independently. You've got the applications, you've got the middleware, you've got the compilers, you've got the operating systems, you've got the virtual machines, and you've got the hardware. And if you do a good job of tracking the versions of all those things, you can try to sort of maintain the wedding cake as you carry it along. And the deeper you go in that wedding cake, the easier it is to carry along, right? So if you're a compiler, if you can't run your compiler in the newest operating system, then you use the older operating system. And if you can't run the older operating system in your hardware, then you stick a virtual machine in there. And I think we agreed that will all work at some level until eventually you have a virtual machine image that isn't going to run on any hypervisor available for the machines that you have. So eventually, at some point, you've got to knock the wedding cake over and start fixing things up. Although there was a general sense that things are getting better in this respect, and I think the first thing brought up was somebody can run their own Commodore 64 floppies on the latest emulator. Yeah, which reminds me, I've got a box of floppy disks I need to try out. There's the Olive project at CMU was an interesting, I think some interesting related work brought up that we could look into and understanding at what level you can do this sort of preservation. And then there was the level of what is it that we really mean by software preservation, right? So at the very highest level, the most long-term thing that you can do is document the algorithm, and as long as you have that algorithm clear by gum, somebody can implement it when necessary. You could preserve the source code and all of your dependencies in their source code. You could preserve the binaries that you built that ran, or you could preserve the whole environment in a box. And I think, frankly, we're trying all of these things simultaneously now. And despite Rob's protestations, I think actually the high energy physics community is perhaps one of the more organized communities I've seen, at least in terms of keeping track of everything built in the proper places.
I made that same point. You guys are more.
I don't know. I can't think of any other project that insists on rebuilding everything every time the compiler sneezes. So it's not as bad as it could be. And then I think we also had some discussion that this is also not entirely a technical issue so much as it is also a community investment issue. Are you looking for?
No, I think that quote has to go on Facebook.
We interrupt this talk.
You didn't know the compilers got sick, did you? And there's also quite a bit of discussion. This is also about community investment. So I believe George brought up that he was just at sort of a high-level DOE labs meeting, and the consensus was that there isn't sufficient investment in the overall software lifecycle. And if you don't invest in the overall software lifecycle, then archival is just one suffering piece of that. Okay, so there were a couple of suggestions on how to attack this. One suggestion, at least for the scope of the research project, was to think about limiting the scope of this problem very severely, at least to get our arms around one piece of it. So just using one particular tool or one particular language and analyze the reproducibility of that aspect. Another comment that came up is that different sorts of technologies have done a better job of dependency management than others. So if you look at a lot of the new dynamic languages, they all have global repositories of packages. And it's much easier and I don't want to pick on any particular language here because that gets you into wars very quickly, but a lot of the more modern languages say, look, I depend on packages X, Y, and Z, and you can go get them from the repository, you download them, make a package, and you're done. And so it might be worth analyzing and documenting the techniques that allow this to happen, not to get into language flame wars, but the techniques that could be applied across languages. There was the observation, which nobody disagreed with, but I guess I don't know if we have data on this, but there's the observation that middleware changes much faster than algorithm and application design. So the preservation of those things has to be defined separately, which I think makes sense to me. But then the provocative question came up: why bother archiving software at all? And the argument was this: people evolve, interests evolve, software evolves, and if the data is of interest and the algorithms of interest, then the software will continue to evolve and have a user community. In 10 years, it will be useful. And if there is no interest or there is no community, the software won't be usable, but there will be nobody there to care about it. So that argument was made. Go ahead.
Sorry, no, go ahead. Finish the thought. I just wanted to get before you moved on to the next.
No, the pushback from the librarians was that it is often not clear what the future value of these artifacts is. That there may be no interest for 10 years, and then suddenly somebody comes back and says some significant interest. And so you may need, maybe one way to balance this is to have some sort of base life support capability so that it's still possible to run these things before the clock runs out on the available platform.
Okay, so I guess I would have turned that around. I mean, the data is not useful without the software, at least from our point of view when it comes to particle physics. So the question really comes down to, does anyone care about the data you're archiving? And if the answer is no, then who cares about the software either? But if the answer is yes, then you have to care about the software. There is going to be someone who's interested in this. Furthermore, the algorithms that are implemented in the software are often general algorithms. That is, that they're applicable at more than one experiment. They could be used at the one you're archiving, but they may also be used at one that's more modern. However, the software as it's written will not be useful at the new one. It will be easier to re-implement the algorithm at the new place. So the software's life is really tied to the data's usefulness.
Yeah, and right. So root is going to be here in 10 years in some form and be able to process these file formats.
Yeah, but
is that high-level simulation tailored to the investigation you're doing?
But root is a very low-level piece of software. So maybe you can read in the floating point numbers you've stored, but you won't really know what those floating point numbers mean.
Well, that's what I'm saying.
All of the software which sits on top.
That's what I'm saying. The low-level general-purpose stuff is likely to have a longer lifetime than the higher things in the stack.
No,
and so right. maybe we need greater attention to.
Okay, I guess I was responding to this idea of whether or not it was worth it to keep the software. Why archive the software at all? And I'm just saying that the software's lifetime is tied to the data's lifetime, at least for our experiment. If you lose either one of them, and you might as well just delete everything because it's no longer useful.
I think there's a scale question here because you guys are talking about 500 programmers and these huge projects, and so it's an all or nothing kind of proposition. I think either if the data is that valuable, you're going to have to make a big investment. Because some of the things that, like I was thinking, at least from our research, is much smaller. It might be a team of 2 or 1. It's easier to redo that from scratch if there's value. So I think there's a scale.
Yeah, no, you would if you were curious. But we're seeing something new at one of these new experiments, and I think this old one, which has been archived, should see it too. So if you go back and you want to look. Oh, the software's done. Okay, well, I'm not going to do that project. Walk away and go do something else because you're right. I mean, with 500 people working for 20 years to produce that software base, that code base, you'll never reproduce it on your own.
Any more questions for software?
Well, I think he had more.
So 2 more.
Wait, did you have a question?
Go ahead.
Oh, I don't want to interrupt.
Go ahead.
Just a minor comment. How you don't, at least in the theoretical literature on this, you don't need to knock over the cake. You just run the hypervisor and another VM that emulates the hardware that was available to run the
Stack them
Yeah, you stack them.
And actually, there's some evidence that works. It's really not quite as grim as
it sounds pretty.
So here's a question. Here's a question which I think is very important. Which software has the greater number of person years invested? Virtualizing the x86 infrastructure, or writing the LHC software? And it's not clear to me which one of those is the winner. I'm sorry.
Software has fewer bugs.
Yes. It's spread over a much bigger base. So, it's well specified. in a certain way that
That
you
the
know,
LIC software is
the
not.
LIC is, because it's used in so many different settings. The one issue though that bears a little thinking about is performance. I mean, for the last 20 years, courtesy of Moore's law, there's actually been a very nice phenomenon. You run this stuff virtualized, or maybe even virtualized a couple layers, and it runs about the same as the original software because you've picked up all this speed up in the intervening generations of hardware. That's probably going to start winding down a bit, and increasingly we're seeing parallel systems to do high performance things. If the software is actually performance sensitive, as opposed to we just need it to run, then there's a whole nother nightmare set of issues starting to emerge about how you emulate a performance sensitive, highly parallelized set of stuff.
There's actually CUDA, the NVIDIA's little blurb that they sent out this last week. Their highlight use case was LHC data analysis on GPU, right? So, if people are moving to those type platforms, then you have to think about how can I virtualize that platform so that in the future that particular analysis would be, doable, right? So it's not just, existing virtualization, it's the virtualization of the futures of technologies that we don't have now, right? Architectures we don't have.
Even the stuff we have now, the parallel distributed computing, that stuff's not as easily done.
Yeah.
There's a lot of catches.
Yeah.
This does emphasize the prior point that you really need a continuous integration testing environment for preservation. If I'm going to keep the software moving forward, I've got to continue to test. If I ever stop, it's going to die.
And I think that's reinforcing, I think what I've learned here today is in order to do that continuous integration, we need a scaled down example.
Yeah.
Let's get a scaled down data set to work with.
Yeah.
And
Yes, what you basically need, and actually this scaled down example will, I think, serve also as documentation for people who come later. Is this scaled down example should start from all the way back from, say, running a simulation, running a reconstruction, making the final end products, which you then can compare with the actual data, and you want it to go all the way through that.
Yeah.
And those are basically the steps that somebody who comes along and wants to use the system to do something new is going to have to follow. They'll modify each step, but the basic form is going to be the same. And so if you have this continuous integration data that's running all the time, the controlling script or whatever will be a documentation.
Okay, so two brief last comments on this. So one was, we've got some suggestions on how to study this abstractly going forward. So one question was to go around and ask a bunch of other projects, what were you doing 10 years ago that you're still doing today, or not doing today, and use that to think about 10 years going forward. And the other one, I don't like this one. The other one was go around and find a bunch of PIs, pick out a paper and say, what would you need to do to reproduce this paper? And then try not to get hit on the way out the door.
Well, that second one is underway, at least within Atlas. In the Atlas experiment, they've given this some serious thought. In the D0 experiment, where I'm working on some of the data preservation, because that experiment has ended and we have to do the data preservation now. Yeah. We already have a group which is repeating one of the analyses with the idea that we get to the point where we have a nice contained script that does the analysis start to finish. Yeah. So, you may not like it, but I think that's also, you have to do it.
It has to be best if it's done at the time of duration.
But doesn't that get back to the question that you asked earlier about is reproducing some project or some experiment actually what's the expected use case? So if that's not the expected use case, that may not be the direction you want to go.
Right. So I think there's a distinction there. The activity is the same, but the objective is different.
Right.
Right? It's one thing to say, I need to get a setup working and I want to verify it against a known result before I start changing it to do something else. Right. And that's a somewhat different objective than saying somebody went out and did that grand thing and now I want to rerun it so I can make sure they got the
Yeah,
right results.
You know, one of these
In which
experiments
the
produces
the former can be small and the latter can be big. Yeah.
So we produce thousands of papers that comes from one of these experiments because they run for 15 years or more. In the case of the LHC, even further. The idea is you take a couple of different exemplar papers which produce results which will exercise different parts of the system. So maybe 3 or 4, and those are the ones that you freeze dry and then run continuously. And then somebody comes along and they say, this is a new signal. Sorry, well, this looks a lot like this particular process because that's also another, a jet paper to start modifying. So you don't try and preserve all, 500 papers or whatever.
So I think that's all we had on software preservation.
That's great, and that's terrific discussion and moves forward the next DASPOS workshop. And maybe the data curation challenge itself. Do we have any other questions of roundtablers in specific, or if we are ready, we can have a few minutes with Clifford Lynch for a wrap up, and then if you want to join and dine around with Katie, or have an ad hoc recommendation for an alternative restaurant, we can figure out if anyone wants to continue their conversations off-site at dinner time. If not, I think without further ado, we'll let you give us a little wrap-up from the perspective of the party.
I will be very quick because it's late, and I'm actually really regretting not hearing all the report outs because I misread the times a little bit and would have come back in here sooner. I want to just open with an observation that if you listen to those first 2 panels, there was a certain sense that, the talks were all over the place. Because, as, I think you beautifully presented, there are a million different slices of this problem, this general problem of preservation and the frameworks around it. And it makes it very hard in some ways to make progress at the level of generality that they were talking about there. And actually, after you went into groups, they went into this sort of abstraction of these, very general purpose research objects. And I mean, it's interesting stuff, but I'm very skeptical that it turns into functional preservation tactics anytime soon. Just because of the really almost intractable level of generality. I'm really interested in the conversations I heard here because they are quite specific about some specific scenarios, and a lot of them are about documenting activity around an instrument over its lifespan, or a project that may involve a series of interrelated instruments, or an observational campaign or something like that, as opposed to taking, I don't know, reference data of various kinds that flows in on a regular basis, as you see in some other scenarios. And really being able to focus on some of these issues about how long do you need it for are very real. The software preservation problem is one that everybody's been vigorously avoiding for decades, other than hobbyists, frankly. The hobbyists are really into it, but everybody else hates it. I was very interested, you mentioned that the Department of Energy is sort of saying, oh yeah, we have a software lifecycle problem, because the National Science Foundation is also standing around saying, oh yeah, we have a software lifecycle problem. And I'm aware of at least 2 substantial projects that they have funded recently that are producing reports elaborating on this. They, in particular, have problems that they like to fund software and then refuse to fund the maintenance or migration of the software to new platforms. It's a fascinating sort of a situation. I think that one of the things that's very interesting about some of the high energy physics situations is just the sheer scale of it. If you look at some of the other scientific areas, you can see something that represents, a piece of software that represents 3 person years. So worst case, assuming you've got the data documented and the algorithms documented, for 3 or 4 person years, you could rebuild the whole thing from scratch. That's actually doable if you want to do it badly enough, and assuming it's reasonably documented, you could probably do the second version a lot faster, like if you go to the source code. When you start talking about systems that represent, 1,000 programmer years, which certainly are the level of the stuff you're talking about, that's a system that, no single person understands or can reproduce. It's a system that's so complicated that the kind of barrier to entry of just understanding what you have there again is huge. And the only way you reproduce that is through some kind of massive organizational commitment. It would have to be very, very important to rebuild one of these software systems from scratch. And I think actually, it's hard for me to believe in most cases it would stand up to competitive funding situations. That'd just be my guess. So I think some of the challenge is how you scale these things down, into a sort of a hibernation mode at the end, because you never are going to be able to reestablish that base. I mean, you only get one shot on it, and I think pursuing some of these very specific conversations is hugely fruitful. Really hasn't been done in depth in any area that I know of. So much of the conversation is at this sort of high degree of general vagueness. So I think you've got an opportunity here to really actually reach some significant conclusions. I would put out a couple of questions. One of them, that just came up was this question about emulation. Emulation technology works pretty well, but it works best when your assumptions about the platforms are relatively similar. You can emulate a one or a few processor CPU on a one or a few processor CPU. If you're looking at a million core machine, you've got to think about, that's not sort of a direct emulation on a single chip. It's a different kind of a problem, and I don't think that's been well studied at all because it hasn't been an issue until recently. I think I'd make is it's probably worth a little discussing, and maybe you've done it already and I just missed it, about how genuinely long you need to keep some of this data, what your expectations are. Because I think that if you're looking at very short time horizons, that's largely about reproducibility and this kind of thing. Somewhat longer ones are this kind of reinterpretation process, or going back and looking for a new phenomenon. I don't know whether this is the kind of data you need to keep for a really long time. Certainly if you talk to people who do weather or biodiversity, they're thinking these are irreplaceable observational data that you need to keep forever, and they think in those terms. do you really need to keep some of this stuff sort of beyond the living memory of the people who built the gear?
You want me to answer?
Yeah.
I can say something. We actually have given some thought to that, and like everything else, it depends on the experiment. So if there's another experiment that's bigger and better that's coming along, it will wipe out the usefulness of the earlier data. So the earlier data has a much shorter lifetime. So in the specific case that I'm working on, the Tevatron's case, the LHC has come along and wiped out, or is in the process of wiping out most of its usefulness, but not all. There are some edge cases where we could do better. So our goal is to make sure that the Tevatron data stays around long enough for the LHC, if it makes a discovery or something funny shows up in the LHC that we might have seen back here, we can go back. So that's a time frame of 10 to 15 years. So we have a definite time frame. And in fact, this is also partially helped by the lab that's saying, we really have no money. Science is getting cut everywhere. How long do you want us to save this data?
Now, 10 to 15 years is a pretty practical thing. You get into 100 years, and now you're starting to talk about the engineering technology has all shifted.
Yeah, so we're definitely, we've made the project so far has made a conscious decision not to talk about, really future-proofing it in a way that, I want this book, which I can read now. I want to read it 100 years from now. And I think in Atlas, similar conversations have probably happened, although the time frame is longer, but the active time frame is also longer. So there may be a technology transition. The experiment will have 2,000 programmers available to it to help it go through, whereas D0, the Tevatron, there's a technology revolution. There's nobody there to help it go through that.
The other thing about the LHC though is it's probably the last large hadron collider machine there will be. So in some ways, we won't ever have another one of these things, at least.
And that's what came out of the first DASPOS workshop at CERN, was that concern that it becomes if it isn't superseded, you start saying, we're going to have people actively interested in continuing to mine this data.
So it's a little bit of a difference.
Yeah, so that's a good point. So for the LHC, it may well be even longer.
Right.
Where you do have to deal with these technology transitions and emulation on hypervisor.
But I would say, Cliff, I thought your comment was very interesting, because I'm not sure if you walked in yet at the point where, was it Doug maybe was commenting on the disagreement about how long one maybe ought to keep things. And I know that it is true that, speaking with my librarian hat on, we see all the time people interested in things that the original people who created it, never imagined they would be. I mean, that you, in some ways, we want to turn to the current, scientists to ask them these questions, and on the other hand, you want to kind of turn away from them and say, you really don't know, you don't have the perspective to understand that. But I do think there is this issue of a need to somehow split. As I've learned about the high energy data, it is of such a different kind. As you say, when you talk about, I think I certainly see a lot of scientific data where you really could say, we can keep it in the same way that libraries keep all sorts of things, where in fact it's not quite in the form you need it in. You're going to have to put some work into it, right? Anyone who uses archives has to put a fair amount of work in going through them. We do not describe every single bit of it. It's up to the researcher to say, what do I think is going to be important? We in some ways can't imagine what someone might want to use it for. But this data is of a different kind. And I think we have to start not making generalities about what we do with scientific data, because some of it is of a kind where you could say, you know what, you could recreate what you need to analyze this data. Or the data itself is in some ways, actually there's a there to it, that you could do a completely different thing on it because you've actually got data you can look at. This data is so tied up with its software. It's like there is no there, and it's really of a different type. And I think I'm starting to see that there really are very different approaches and solutions probably needed for different types of scientific data.
Well, it's also tied up, this is very engineering mediated data.
Right, exactly. That's what I mean by there's no there to it.
Imagine you were trying to build the LHC using the engineering base that existed in 1910.
Steam.
No integrated circuits.
With that, did we cover all the bases today? Thank you.
I gotta say, this bit I got to eavesdrop on here was one of the most interesting conversations I have heard about, the curation of critical scientific data, and I hope I get an opportunity to come eavesdrop some more.
So I'll ask everybody who wrote up a summary of anything. Email it to Natalie? No, Natalie? Kelly.
Yeah. Mm-hmm.
Yeah.
Yes. If you need my email address, if you don't have it, if you have something quickly to jot it down, it's KOCONNE and the number 8 at nd.edu. And you can find me at crc.nd.edu at the people page where there's also
Right,
DASPOS.org. Okay. Yep.
It's also very good to thank Kelly for helping.
Yeah.
Thank you.
And Natalie includes some of them.
Jerusalem.
Okay, so